The strong form of the third law of thermodynamics posits that as a physical system approaches absolute zero, its entropy vanishes. This law relies on continuum mechanics, assuming that when dynamical motion ceases, the entire state space of the system must collapse to a single, unique point. W-field ontology models the universe as a discrete, token-mediated substrate. In this framework, structural requirements for the third law are absent. At absolute zero, transition updates have arrested. But while motion stops, the substrate remains locked in a multitude of valid geometric configurations. Classical physics commits a continuum projection error here, conflating the arrest of transitions with the uniqueness of the resulting state. Within a discrete substrate, zero temperature does not require zero entropy. To demonstrate how residual entropy survives absolute zero, we must move past continuous phase space and examine the discrete lattice axioms. Rebuilding thermodynamics begins by replacing continuous spatial dimensions with an admissible discrete base domain. Axiom 2.1 defines physical reality as a structured graph, a tetrahedral lattice of valid sites, rejecting the mechanics of a continuous vacuum. Under Axiom 2.2, local dynamics consist of discrete token exchanges between these nodes. Force fields are replaced by specific transfer rules. W-field calculus replaces differential flow with recursive, localized step evolution. Each movement is weighted by the local token measure. This eliminates infinitesimal states. Motion becomes a series of binary, localized jumps across the lattice. In classical models, energy can bleed away in infinitely dividing fractions. In a discrete ontology, a system either possesses the tokens for an update or it is static. Because the fundamental nature of motion is a discrete jump, the process of a system cooling to a stop follows structural rules that differ from those of a classical fluid. Next, we must define what constitutes a physical state within this discrete graph. Why toposemantics defines a physical state as a token-realizable section mapped over a discrete boundary, a W context, rather than a coordinate point in a continuous phase space. Global states emerge through the W sheaf condition, which requires the lawful gluing of these local contextual sections. Physical truth is determined by contextual realizability. States exist only if their token configurations are compatible across the lattice. When observed, this becomes the macroscopic regime, an emergent property where one regime can arise from many distinctly different underlying token configurations. A macroscopic reading of 0 degrees provides no information about the underlying geometric uniqueness. Mathematically, this allows for high plurality at the floor. We define W entropy as admissible multiplicity, the count of valid global lattice configurations that project to one macroscopic regime. In this framework, the zero temperature limit is defined solely as the condition where recursive token updates are maximally suppressed. This limit restricts transition accessibility. It is a statement about what the system can do, not what the system is. The classical third law assumes that suppressing these transition pathways forces the multiplicity counter to 1. However, the gluing laws of the W sheaf do not mandate that halting token jumps retroactively eliminates compatible lattice configurations. Therefore, a system can reach total internal transition arrest while maintaining a massive multiplicity of geometrically valid structural configurations. Theorem 5.1 formalizes this. Zero temperature is not a uniqueness theorem. Reduced update accessibility does not imply a singleton global realization. The continuum projection error becomes visible when comparing the two models. The visual funnel of continuous phase space suggests that stillness requires a single point. W-field calculus shows that in a discrete graph, nodes remain illuminated even after the connections are turned off. This set of remaining states is the floor sheaf, the subsheaf of token configurations that remain realizable in the zero update limit. Proposition 6.2 states that if this floor sheaf admits more than one global section, residual entropy is non-zero. A zero entropy floor occurs only in the special case where the floor sheaf is a singleton. It is a specific outcome, not a universal law. Residual entropy is the generic, expected result of a system where structural floor realizability is plural. Principle 8.1 replaces the third law. The entropy floor equals the multiplicity of frozen, globally realizable sections compatible with the macroscopic regime. This requires thermodynamics to be rebuilt on the basis of contextual realizability, where abstract equilibrium becomes secondary to lawful realizability under discrete rules. classical models fail by mistaking the cessation of motion for the collapse of the state space. Zero temperature does not imply zero entropy. The suppression of updates does not force the uniqueness of the global state. Absolute zero reveals a vast, complex multiplicity frozen in geometric permanence, a departure from the classical image of an empty, singular point of dead matter.